Hello everyone, welcome to the course on architectural design of ICs. So, today we will see the FFT architecture. So, FFT means the fast Fourier transform. This is one of the most commonly used blocks in mainly for the digital signal processing. So, it has wide application like in image processing or in wireless communication or in video processing. So, to design the hardware for let us say for video processing or for audio processing or for image processing, you need to design the FFT block. Okay. So, for that reason you have to know about the FFT architecture. So, today we will see in this particular lecture we will see the FFT architecture, what are the architectures are already there and still people are trying for several decades to design one efficient architecture for a fast Fourier transform. That means, why I need this efficient means actually some of the architecture is related to increase the, that means the computation time, or sorry not that means to decrease the computation time, so that the throughput of the FFT becomes much more on the higher side. That means, we can process it very faster, as well as some of the architecture has basically designed with respect to that means for the low power application. So, as FFT means we have to actually there the memory access is much more. So, how to reduce this memory access so that it can becomes, or this will be much more applicable for low power applications. Okay. So, those type of architectures are already there. So, various kinds of architectures is already available, but we will see just the basics or the, that means very few basic architecture of FFT in this particular that means lecture series. If you want to know more, that means if you are more interested on FFT architecture, the present days you can find it in IEEE websites, or you can find it in that means Google Scholar, or if you that means if you are not getting it, then please let me know, then I will definitely I will provide the corresponding information about the recent days FFT architecture, how the people have already developed or still people are basically trying to develop this high performance, highly efficient FFT architecture. Okay. So, the first actually we have to consider this Fourier transform which came for digital signal processing is this discrete Fourier transform. So, this is the that means equation for this generic discrete Fourier transform. So, whenever we in actually it the Fourier transform has been started with this discrete Fourier transform, and whenever we have the people have tried to design this DFT. So, at that time the baseline for this computational the hardware requirement, that means the computational complexity of this DFT requires n complex multiplication and n minus 1 complex addition for one n point DFT. In all n DFT coefficients requires n square number of complex multiplications and n into n minus 1 number of complex additions. Okay. So, therefore, the complexity in terms of real operations, it requires 4 n square number of real multiplication and 2 n into n minus 1 real addition. What does it means is that to implement this particular function, suppose for n point DFT, I need the computational overhead, that means the hardware requirement for this to design one n point DFT, which is the requirement is 4 into n square. Let us say if I want to design one 8 point FFT. So, at that time, so 8 square means 64 into 4. So, 256 number of real multiplications I need, as well as so 56 into 2 means 112 number of real additions operation I require. So, if I consider that 8 point FFT and the FFT length of each of these 8 bit. So, at that time it requires a huge number of hardware requirement. Okay. So, this as we actually use more number of hardware, that means more number of multipliers and more number of addition operation. So, at that time this will consumes more power as well as the speed will be also on the lower side. So, that is why people have actually in the earlier days the DFT actually it has been done in decimation time. So, in decimation time we have just divide the DFT into two part, where this is basically the half of this is basically done considering this n by 2 point DFT, and the lower portion is done by on n by 2 point DFT. Okay. Now, the thing is that after actually dividing the these coefficients into even and odd, we can do this butterfly operations, which is basically related to the corresponding Tweedle factor multiplications, which is very much related to this particular term, which is e to the power j 2 pi by n into k n. Okay. So, now for these two n by 2 point DFTs, we need 2 into n by 2 square number of complex multiplication as well as 2 into n by 2 number of 2 square number of complex addition. So, combining these two that means DFT outputs, we can get, that means which requires total number of n complex multiplication as well as n complex addition. So, the total complexity at that time it becomes n square by 2 plus n number of complex multiplication and n square by 2 plus n number of complex addition. So, now in this particular case, if we consider that okay, we need that means 8 point FFT again we consider. So, at that time 32 plus 8. So, 40 number of complex multiplication we require. If we actually divide the coefficient, that means if we divide this the corresponding that means sample in even term and then odd term, and both if we do the, that means if we run this computation of the DFT in parallel. So, at that time the requirement for this complex multiplication and complex addition, they became little bit lower than the original actually DFT implementation. Okay. So, actually this is if we consider only about, that means radix 2. Radix 2 means as we have only divided two part, that means the even part and then the odd part. If we increase the radix, that means if we consider 4 parallel DFT which is running at n by 4 point DFT. So, at that time the corresponding actually the computation time, that will be much more faster. Okay. So, we will see how this actually the computation time at that time becomes lower whenever we consider more of the radix, and if we consider more of the radix, then what also it that means what it happens, then that will also we will also see. Now, depending on this actually 4 point the radix 4 DFT in decimation in time, what we can do is that we have actually in this particular n by 4 point DFT, what we have considered? We have considered x 0, x 4, x 2, x 6, x 1, x 5 and x 3, x 7. Then they are being basically, here we are doing this butterfly operation, which is nothing but this Tweedle factor multiplication, which is coming because of this e to the power j 2 pi by n, because of this that particular factor. So, whenever we will do at that time that corresponding functions, it will give you two part, one is the real part and one is the imaginary part. Okay. So, in this butterfly operation you can see that this particular actually node is multiplied with the coefficient values of 1 and this particular actually branch or this particular edge is basically multiplied with the term of minus 1. Okay. So, these values of 1 and minus 1 they are being calculated or computed based on the corresponding twiddle factors. Okay. So, now and this will be actually repeated until and unless we are getting these 2-point TFTs. So, this is another example of this decimation in time, this fast Fourier transform, and basically fast Fourier transform is nothing but this division of this n by 2 point FF, that means DFT in that means if we divide this to, that means odd part and the even part, and then if we run them on parallel computation, that is the and by that technique we increase the computation, that means we increase the throughput of the Fourier transform, which is nothing but this fast Fourier transform. And whenever we do like this, so at that time the complexity becomes n into log 2 base n number of complex multiplication and addition. Where what is this n? N is nothing but the corresponding number, that means the point, that means n point DFT or n point FFT what we require. So, in this particular case, as we have considered 8 point, that means FFT. So, at that time the corresponding complex multiplication and the addition requirement will be 8 into log 2 base n equals to, that means 24 number of complex multiplication and addition operation. And here you consider each of these is basically requires this multiply and accumulation, that means operation. Now, what is this butterfly computation? So, the butterfly computation is that it actually generates from the m minus 1 stage, it has to multiply it with the corresponding twiddle factors to generate the next stage, which is the mth stage. Okay. So, in this upward, actually this upward, that means branching, it has to multiply it with w dash w r n, whereas this lower branch has to multiply with the twiddle factor values of w n r plus n by 2. So, what we can do, this upper branch will be actually depending on the this value, if we know the n. So, at that time we know what will be the values of this w n and w n r plus n by 2. So, from there we can we know that this lower branch will be, this value of this will be minus 1 and this value will be the 1. So, the final actually complexity for decimation in time FFT will be, if we consider this kind of butterfly computation. So, at that time it will be n by 2 into log 2 base n complex multiplication and addition operation. So, that means, in the earlier case, in this case actually we are having 8 into 3 for 8 point FFT. So, 24 number of complex multiplication and addition operation. So, if we just constitutes this butterfly unit and if we actually use this corresponding this the twiddle factors values as 1 and minus 1. So, at that time the requirement for this multiplication, complex multiplication and this addition will become 4 into 3 means only 22, sorry only 12 at that time. So, in actually decimation in time flow graphs require two sets of registers, one for the input and the other for the output for each stage. And note the arrangement of the input indices are in bit reverse indexing. Bit reverse indexing means actually the output, if I apply this input at x 0, x 1, x 2, x 3, x 4, x 5, x 6, that means this is the input sequence, the output from this decimation in time FFT, the output will become in a bit reverse manner, which is nothing but this x 0, then x 4, then x 2, then x 6, then x 1, then x 5, then x 3, then x 7, something like this. That means 0, this will. So, this decimation in that means FFT algorithm. So, this is the initial DFT the equation. Now, if we split this DFT equation into even and odd that means frequency indices, then this particular equation can be written as n 0 to n by 2 minus 1 summation of this n 0 to n by 2 minus 1, where x n into w n into n to r, whereas that means this is the even part and this is the odd part. That means the DFT now it has been split into 2, so that I can run parallelly. Okay. So, then this the corresponding graph for this decimation in time, decimation in, this is the earlier one was the decimation in time. So, this is for decimation in frequency. So, in decimation in frequency, what we have to give is that the input should be in order, whereas I will get the corresponding output in the bit reversed manner. So, that means this is not the so x 0 is producing x 0, the x 1 is then it is producing x 4, x 2 is producing x 2, x 3 is producing x 6, x 4 is producing x 1. So, something like there, the output will comes in the bit reverse manner. So, at that time to get the output should be also like x 0, x 1, x 2, x 3, x 4, x 5, something like that. So, you have to do some bit reversing, you have to, that means you have to do the bit reversal, so that this particular sequence became in order. Okay. So, in decimation in time, actually then this DIT, that means decimation in time structure, with the input bit reverse, the output will be natural. That means, if we apply the input in a bit reverse manner, which is this x 0, x 4, x 2, x 6, x 1, x 5, x 3, x 7. So, at that time the output will be comes in the bit reverse manner. So, that means you can do in that means in either you can put, either you can give the input in the original sequence, you get the output at the bit reverse manner, or you put the input in the bit reverse manner, so that the output comes out from this that FFT block, which will be in original or in original sequence or in particular order. Okay. So, and here you see all this, that means this particular the lower branch, they are basically multiplied, this butterfly, this cross multiplication is known as the butterfly operation. So, the butterfly lower branch of this butterfly, they are being multiplied with -1, whereas the upper branch has been multiplied with +1. Okay. Now, whenever this in, so this is in decimation in time, and in case of decimation in frequency, the input is in original sequence, but the outputs are coming in bit reverse manner. So, here you see the difference is that initially actually we do this, that means the radix 2 butterfly, okay, and then actually it has to multiply with initially the x 0 with x 4, then x 2 with x 6, x 1 with x 5, x 3 with x 7. Then in the next this x 3, x 1, x 7, x 5. So, it has to multiply with that. Then again this x 1 has to multiply with x 0, x 5 we has to multiply with x 4, x 3 has to multiply with x 2, so x 7 has to multiply with x 3. Okay. So, which will be just reverse in case of decimation in frequency. Okay. So, in decimation in frequency case, so the initial computation will be x 0 with x 4, then x 1 with x 5, x 2 with x 6, x 3 with x 7, and then we will get the corresponding output something like this. So, the decimation in frequency FFT algorithm, it has to actually this is a method to avoid, that means what method we will, that means adopt to avoid this bit reversal in filtering operation is the compute the forward transform using natural input and bit reverse output, and this multiply this DFT coefficients of input and filter response, compute this inverse transform of the product using bit reversed input and the natural output. Okay. And now, so whatever we are considering, that is only for the forward DFTs, okay, or forward FFT we have only considered, but what about the inverse FFT? Okay. So, what will happen if we design the IFFT block? So, at that time how we can do, that means how we can modify the FFT code so that it becomes the inverse, that means inverse first Fourier transform. Okay. So, what we can do is that at that time it will be just 1 by n into k, that means k 0 to n minus 1 with x convolution with this w n into n base k n. Okay. So, how we can basically design the hardware for this is that so actually this is yes. So, here you see initially what we are considering is that we are considering n.2 DFT, and then we are basically multiplying this with each of these Tweedle factors. Now, here in decimation in frequency FFT algorithm, so what we have done is that we have initially we have done this x 0 multiplied with x 4, x 1 multiplied with x 5, x 2 multiplied with x 6, x 3 multiplied with x 7, and then each of these in the next stage we are having this n by 2 point DFT, and here we are having n by 2 point DFT, which basically generates this x 0, x 2, x 4, x 6, and here x 1, x 3, x 5. That means, all this odd even part here from here, and the even odd part from the lower DFT. Okay. So, then the same things using, that means n by 4 point DFT also we can easily compute, just it is just the reverse case of the that means this first Fourier transform what we have already seen. So, the decimation, that means this actually the DIT butterfly, if you see, actually it corresponds with this x 0 and x 4, whereas this decimation in frequency they are being multiplied with, that means in the, here we are considering the input in the bit reversed manner, but here here we are considering in the original sequence, but here we have to consider the inputs in the bit reverse manner. Okay. So, this is the corresponding actually this decimation in time FFT structure, and this is decimation in frequency structure. So, here you see, here we are considering x 0, x 4, x 2, x 6, x 1, x 5, x 3, x 7, but here the inputs are already in sequence. So, the major difference is that whatever we are getting, that means the inputs are bit reverse manner in case of decimation in time, the outputs are in the original sequence. Just the opposite, in decimation in frequency, the inputs are in the order, but the outputs are in bit reverse manner. So, by seeing this, I can say that that corresponding FFT architecture, whether that is following decimation in time or decimation in frequency. So, this is another actually alternate FFT structure. This is the basic FFT structure what people have designed in the earlier days of FFT computation. Okay. So, in all this case, we have already actually know that in decimation in frequency, the input in decimation in frequency, the input should be in the corresponding original sequence. Okay. Now, so actually whenever we suppose consider one 6 point decimation in time FFT. So, at that time what will happen? So, initially in the earlier example we have considered that 8 point FFT. But if we consider this 6 point FFT, so at that time what will happen? We have to consider this x 0, x 2, x 4, whereas the odd part are x 1, x 3, x 5. So, this x 0 is multiplied with x 2, and then this again it is multiplied with x 4. Here x 1 is multiplied with this, that means it is the butterfly operation with the x 3, and it is the butterfly operation with the x 5, and we give the input in the bit reverse manner, we get the output in the original sequence. Okay. So, this is that means this decimation in time first Fourier transform architecture. Now, actually whenever we have to design this particular circuit, so at that time the hardware implementation, this is the flow of, that means how this data flow diagram of this first Fourier transform. Now, this I have to convert, or this data flow diagram will be implemented via some hardware. So, what will be the hardware or structure to implement this particular data flow diagram of this first Fourier transform, that we will see in the next lecture. So, thank you for today's lecture.